That's the title.
Well, we'll give it a couple of minutes.
Right. I know Yatir knows. I think, yeah. Even David. The small audience.
See, this is what happens when you don't post a title. So who's speaking next time? Is it Ali?
I don't know.
Ali, yes. Is he there? I can't identify people in the room.
Some people are coming. I know.
One or two. Okay, Christian. I think we have some non-model theorists here to listen to you and some model theorists. So let's go ahead. I'm very happy to have Christian Delbé, who is going to tell us about DP minimal expansions of Z plus.
Thank you, Deirdre, for giving me this opportunity. So this talk will be about DP minimal expansions of Z. So I will define all the expression in this title. I think this is known. I will give a lousy definition of DP minimal and of expansions for non-model theorists, and then we will try to see why it has been an interesting subject for the last 6-7 years. Yeah, in model theory, it was an interesting program. So I will start with basics, and then we'll have, I mean, the real talk will be on a conjectural classification of DP min. Okay, will be DP minimal expansions of this group, and I will add question mark because it's not completely clear. Is it too low? Okay. Right. Yeah. Okay. And like this. Right. So let's start with basics. First, a structure. For us, a structure will be a structure on the set of integers, right? It will be something of the form. So we have the integers as a set, and then some relation symbols, function symbols, and some constant symbols. Though for us, constant will not be that important. We'll see why in a while. So for each relation I, it defines a relation on the Cartesian on some Cartesian power of Z, which is called the domain. This will be the arity of the relation, and also the function that we'll consider are functions from some Cartesian power to Z, to the domain. Okay, and constant are just fixed elements in the domain. Okay, so basic example which we will follow for the whole talk, because it's kind of the most important one for now, is this structure which we call Presburger arithmetic. It's really the structure of the ordered abelian group, in which you have a binary function symbol and a binary relation symbol. Okay, sometimes you want to add the 0, but we will see. For us, the constant will not be important for some reasons. It will be clear. It's not moving. Okay, so okay, I'll go there maybe first. Okay, so I want to give a good intuition of what definable sets are. In model theory, we are instructed on structure, and structure, more importantly, what are the definable sets in a given structure. So this will be given by the setting of first order formulas. So each structure Z, we have a language associated to it, which is basically this data with the arity of the functions and the arity of the relations. Okay. Yep. And so how do we construct the formulas? So it's really about expressing properties in this language. So with free variables and all this, and with one specific thing is about the quantification. So the basics will be first that we have terms. So the formula in variables x1, xn is a property expressed in the language L with some restrictions. So for us, the terms will be applying functions to variables x1, xn, and constant. Okay. So for our favorite example, how do you do terms? You just do expression like this, like x1 plus x2 plus x2, which is, we will write it x1 plus 2 x2. And also we allow every parameter in the language in the terms. So 3x plus 7 is a term for us. all of our structures. And then we do basic formulas, which are some term equals to some other term, so T prime of x. So this is like equations. This will be a formula. This thing will be a formula in this language, and then we apply Boolean combination. So this will be yeah, and also the relations, right? So x lower than 0 is a relation. So r of t1 of x, tn of x is a formula, and then we apply Boolean combination, so which are conjunction, disjunction, sorry, x, and negation, right? Not phi. So we have also inequations in the available properties, and then the last part, which is an important one, is apply quantification, which are for all, and there exists. So once you have a formula like this, phi of x, y bar, and you want this expression to be also a formula, x, y bar, there exists an x phi of x, y bar, and this quantification here will be over the whole domain, which means that there exists a y, x equals 2y plus 1 will be a formula in first order logic, but in this structure, this quantification is over the whole model. That's all. Which means that this is a formula phi of x, and then if you look, if you want something in, yeah, z will satisfy this formula in an element, to satisfy phi of a. By definition, I say this means that there exists a y in z such that a equals 2 times y plus 1. Okay, and so if I look at then I okay, so these are, yeah, okay, these are expressions, and these properties are constructed in a bit restrictive way and make sense in a given structure. And the idea is that this formula will define subsets of the structure. So the definable set D in the structure Z, which is again something like this with the language, is a set of realization of some formula in the language. So D is a subset of Z, of some Cartesian power Z, and there is a formula with phi of Z1, Zn, such that D is the set of tuples A1, An in Zn, such that A1, An satisfies this formula in the structure Z. And An, yeah, phi holds when replacing the variables by this holds in Z. Okay, and so we write this phi Z phi of A1 An is satisfied in Z. Okay, so this is a bit of the boring part, because we don't really care about how formulas behave, but more about what is a definable set and what is not a definable set in a structure. So we will look at a given structure together with its family of definable set. It's kind of endowed with its family of definable set. So def of some structure Z, which is again Z this, is the set of all definable sets in Z. And so it's a subset of the union of all the Cartesian powers. Okay. Okay, so let's look at some example. For instance, in Z plus in the Presburger structure, N is the set of realization of the formula set of A such that A is greater than 0, right? So it's a definable set. This is a bit of a silly example, but yeah. And so with this notion of definable sets, somehow we would like to have a way of talking about two structures and the relation they have between each other without regarding formula and only with the kind of the power of all definable sets in it. So this is the notion of reduct and expansions. So let's Z1, Z2 two structures on Z, and we say that Z1 is a reduct of Z2, or Z2 is an expansion of Z1, so reduct expansion, by which we mean that the definable set, the class of definable sets in Z1 is a subset of the class of definable sets in Z2. Okay, so what's an example of this, for instance? So let's try to show that this is a reduct of the ring of integers. So how would you define this relation? Here we don't have a relation in the language, but what I'm saying is that in the class of all definable set here, I contain every definable set here. Of course, everything which is defined by plus is also defined here. But it's not hard to see, if you think about it, that you only need to check that this is definable in this structure. It's a definable set in the structure. And it's a binary relation, so it's a definable subset of Z2. Let's try to show this. So what I'm claiming is that X is less than Y. This is equivalent to there exists, or let's say less than or equal to X1 to X4, such that X plus X1 squared plus X4 squared equals Y. So Y, so this is indeed a formula in this structure, because I can multiply variable by itself. I have the multiplication, and then I have only sums, and quantifier are given over the whole models. And why is it equivalent? It's because every natural number, every positive number, can be written as a sum of 4 squared. So that's a way of seeing that every definable set here will be also definable here. I will write Z1 is interpretable with interdefinable all this like this if it's a reduct and an expansion. In other words, if the definable sets are the same. If this, yeah, okay. If def z1 equals z2. So there is something which can happen is so this defines an order, right, between structures, the partial order, and sometimes we have a consecutive element in this order, and this is what we, or at least I call minimal expansion. Expansion Z2 of Z1. So Z1 is a reduct of Z2. We say that it's a minimal expansion or equivalently a maximal, or like Z1 is a maximal reduct if for all structures Z3 such that Z1 is a reduct of Z3, which is a reduct of Z2, then Z1 is equivalent to Z2, 3, or Z2 is equivalent to Z3. It just means that these two structures regarding the definable set, there is a gap between them because there is no, they are consecutive for this order. Everything which is definable in an intermediate structure will be either definable in Z1 or in Z2. Yeah, we say like there are no intermediate structures, or just it's like a consecutive structures. Okay. And this actually this exists. For instance, there is a classical example. It's not the oldest one, but it's a nice one I found. Marker 1990 shows that so of course I'm fooling no one when I'm saying that a structure is not only on Z but can be, is a very general notion. But Marker proved that the field of the complex together with the predicate for R, this expansion is minimal. There is nothing between this and this. And this is interdefinable with only the real field. So it's kind of, there is nothing between, I don't know, algebra and analysis. I don't know. Okay, so minimal expansions. And we will see more examples of this. What else do I have to define? We are almost done with the basics. Is it? Am I on time? I'm on time. Yeah, so I want to define notions of stability and NIP and DP minimality. So in model theory, we are very much interested in understanding structures, and for always, right? So the class of definable set, how is it tame? For instance, quantified elimination is a result that tells you that the class of definable set is actually closed by projection. So you only kind of need to understand the Boolean algebra instead of this class which has which asks for projection. But yeah, so quantified elimination is a way to understand how well behaved is a structure. But a more modern point of view consists in applying some combinatorial constraint on the whole class of definable sets. And this historically came with, has been very, very developed in the context of what's called stable formulas or structures. Okay, so I will give an almost definition, which is because I didn't define exactly what how model theory is interested in the whole theory of a given structure. So I will give kind of loosey definition, so stable formula in a structure. It's a formula phi of xy. So I have two tuples of variables. Okay, and I say that it's stable if there is no infinite sequences. And I'm not saying on purpose where I take these sequences, but you can imagine I take them in the domain such that in the structure, let's say Z, such that Z satisfies phi of AI bj if and only if I is less than j. So I call a formula stable if this configuration does not never occurs. So we can see it a bit. So let's say A0, A1, B0, B1, etc. And so I have like these two sequences, and the configuration I'm not allowed to have is if I draw a line every time the formula holds, it will be something like this. It's called a half bipartite graph. And so okay. And this is I choose a combinatorial configuration, and I ask a formula to be something if it avoids this combinatorial constraint. And it turns out that this way of thinking has been very, very successful in understanding structures from a model theoretic point of view. Yeah, so I just want to give you an intuition on what kind of constraints are these stable NIP, all these notions. So for instance, NIP is NIP. If I do the same, but here I say AI big I for a subset of the natural numbers, and then I ask the same thing phi of AI b big I if and only if I belongs to I. And this is what I want to avoid. And then the structure Z is stable if no formula is stable, and same for NIP if no formula if all formulas if all formulas are stable, and NIP if all formula are NIP. Okay. Yeah, for an example, of course, of formula that satisfies this kind of thing is in this structure. The formula x less than y will not be stable. Okay, so this structure is not stable. It turns out it is an IP. And just a quick word about the minimality. It's some kind of minimal notion inside an IP. It's kind of an IP of dimension 1. But it's already, I mean, NIP structures is a very wide class, and already DP minimal structures are we have a lot of examples and a lot of natural examples. DP minimal. So DP minimal is dimension 1 NIP structures. Okay. Yeah. So I'm sorry, I'm not defining more than that, but I won't have time otherwise. Okay, so now we can go to the interesting part of the talk. So yeah, DP minimal, we kind of know what it means. Expansions of Z, so it's all structures that will you add some definable sets in a group of integers. Okay. Now, so the question of this question of DP minimal expansions of Z, it all started with a result of a bunch of people. So Aschenbrenner, Dolish, Deirdre, Haskell, McPherson, and Starchenko in 2015. So what they prove is a curious thing. So this structure of Pressburger arithmetic, it is DP minimal. It is a DP minimal expansion of Z. And they prove that Z plus less than has no proper, so proper means proper expansion, proper DP minimal expansion. Proper means that it's an expansion which defines strictly more definable sets. So has no proper DP minimal expansions. And at that time, this was the only DP minimal unstable expansion of the group of integer. Okay, it was the only one that was known. So a natural question that they ask, I'll call it conjecture 1. It wasn't raised as a conjecture, but more like a question, but we'll see. Is every DP minimal expansion of Z a reduct of Pressburger, right? So that was, yeah, more like a question, but that okay. And then other result came out. So by our good friend Gabriel in 2016, there are no, I mean, yeah, okay. So Z plus 0, Z plus, and Z plus this expansion, that's why I will, that's what, how I will write expansions, is minimal. Minimal in the sense there is nothing in between. So here there are no reduct which are strictly between those two. So, and also Conant and Pillay, so I think it's the same year, they prove that Z plus has no stable DP minimal expansion. Okay, so no stable DP minimal expansion. So I should mention also other names. So there was Poisson before, which kind of proves something bit weaker, but Palacine and Skiller. Palacine, yeah. Linus also worked a bit on this problematic, but yeah, okay. No stable dp minimal expansion. So we know what? That there is no, so when you look at this, there is no dp minimal expansion above, there is nothing in between, and this doesn't have any stable dp minimal expansion. So it's very encouraging for conjecture 2, which was is z plus 0, z plus less the, or let's say conjecture 1 prime, the only dp minimal expansion of z plus. Right. Okay, and so this was disproved. I mean, I don't think it was considered true question for a very long time, because it was disproved by Alouf and myself. This, I think the 1 year later, 2017. If you define this order, x, p for some prime, y less prime, if and only if the periodic valuation of x is less than the periodic valuation of y, then the structure z plus less p is dp minimal. Okay, so that's a new one. Of course, it's unstable. We have an infinite order. And it's also minimal. Minimal, so there is nothing here. Yeah, so this changed a bit the conjecture, and at that time there was, yeah. So how can we reformulate the conjecture? We are still trying to understand what are dp minimal expansions. The integers. Okay. So conjecture it's false, but then conjecture 2 is every dp minimal expansion of z plus either z plus less or expand z plus and the periodic order relation. Yeah, because I mean it wasn't sure, it wasn't very clear that we could have the same result here as we had for the order. Yeah, there was some idea of having already some dp minimal expansions of this. But at least like only 2 choices. And this was strongly supported by a result at that time, the Johnson classification of dp minimal fields. So Johnson proved that if you take a dp minimal field K, dp minimal, then it's either something which looks like an algebraically closed field, okay, a real closed field, or has a definable Henselian valuation. Okay, so this kind of trichotomy was really supporting like this. This is actually a trichotomy, right? So the stable case would be z plus, the ordered case would be z plus less, and the Henselian valuation case would be the periodic valuations. Are those the only dp minimal expansions? And so this was actually disproved 1 year later. Actually, 1 year later, actually. Stop the date. Yeah, this would have been nice, but actually it's not the case. So Tran Waldsberg, I think around 2017, actually. They came out with something with a new DP minimal expansions, which were completely different. And okay, and also here you see, so there is only one stable, only one with an order, and like countably many periodic valuations. But they say, okay, so if you define some cyclical order, C alpha of x, y, z, so you have like this character, right, R over z, and you take alpha in an irrational number, and you just project with by shifting by alpha. Okay, so x equals alpha times x plus z. So you have this function, but this is a circle, right? So you have what's called a cyclical order. Psi of A, B, C. When you orient your circle A, B, C. Okay, and so if you do the pullback of this order, so here you are putting z through this function around the circle and twisting it a bit, and you put it back. So C of x, y, z, if and only if C, so C alpha times C of pi alpha of x, pi alpha of y, pi alpha of z. So it's a relation on the integers. And then what they prove is that if you add this relation, is dp minimal. And not only this, so it's a new kind, and they also prove that it's not interdefinable with the other dp minimal expansion that we know. And they prove also, it's nice, they prove that if you take two of them, C alpha and C beta, they are non-bi-interpretable if and only if they are non-Q linearly dependent. Yeah. Okay, so which means that they are uncountably continuumly many bi-interpretable by definable. So that is pretty bad, because then there are much more dp minimal expansions of the group of integers that we expected. And they didn't stop there, actually. This was kind of a bomb, like it was very, very disturbing example. They also proved that, okay, so here I'm not defining this, but some expansion, so people who know what that is, know what that is, and people who don't know, it's just something which expand z plus c alpha. And they show that this expansion, okay, so it's famous to be also dp minimal when you do this expansion. So it's a proper one, and between those two there are uncountably many reducts. So there are even more dp minimal expansions between. Yeah, something I should have mentioned a long time ago is that if you take a reduct of a dp minimal, then it is also dp minimal. Wait, that was the first question. The scalar expansion. So when you add all externally definable sets. from an elementary expansion. Elementary extension, you look at the traces, the induced structure, and you add them as separate predicates. And in NIP, it's very well behaved. Yes.
In your example with Savan, do you know if the Sherlock expansion is?
It's the same. I mean, we never really proved it. At least it's very true for unary set. Okay, maybe not actually. Maybe not. Okay, no, I think not, because I think it's contained in some result of Eric. Yeah.
Right, it's true, or it's the same, or
No, it's not. I think it's not. No.
So it's not
It's not the same. The Scheller expansion of this, I think it's not the same.
because it also could have given another.
Yes, yes, but yeah, of course, of course.
did Eric and then also prove there are redux of the cyclic order?
No, no,
They didn't prove it, or they proved it?
no. They didn't prove that there are, and somebody else proved that there aren't. What they proved, but I will talk about it right now.
Was the united?
Yeah. So this is exactly. Yeah, there was another question. Okay. So there are even more DP minimal expansions here, and it's not even finished. So then, okay, so this was around 2017. So I guess people kind of, some people kind of stopped thinking about it. I know I did, but yeah, then in 2020, a lot of things happened. This was last year. Okay, so first, Waldsberg, he couldn't stop there, and he proved something else. He proved that there are even more DP minimal expansions of this. There are a lot of them, uncountably many, which have this one as a reduct, as a proper reduct. So even above this, so Z plus, I will do a final drawing to understand C alpha, SI, SH, and even here there are a lot of, I don't know how to call them, something with many reduct, and among them the Scheller expansion. And maybe I will come back on this later, but he also, I mean, it's a huge paper he has, where he kind of find a uniform way of finding DP minimal expansions of the integer, such that everything we know, every DP minimal expansion we know, is a reduct of this one. Yes. What time is it? What time do I have yet? Okay. Okay. He also proves that, so it's settled. He also proved that this has a proper DP minimal expansion. Okay, and he construct one, which is kind of funny. He construct one expansion which interprets Pressburger arithmetic. There is a DP minimal expansion of this which interprets, so not defined but interpret. Yeah, Pressburger arithmetic, kind of, because it's the value group. Yeah. So okay, so it's kind of everything which is happening with cyclical orderings. It's a completely new set of the minimal expansions, and it seems that there is no rigidity result between them. Like here, there are a lot of things, and even above there are again a lot of things. whereas we had so much rigidity, right? Expansions such that there are nothing else. They define kind of very rigid sets. And so a way of, so of course the conjecture is completely false, and a way of recovering the conjecture would be except for cyclic orderings, periodic valuation or order. Okay, kind of trying to put aside the cyclical ordering. Maybe it's the only thing that goes wrong, and this is again false. And let's see why now. There is a very nice paper of Tim Clausen. Actually, he has those results for for a long time, like I think in 2018, something like this. I remember he had this result, but he was waiting to have a whole paper. So the paper came out in 2020. Clausen, student of Catherine. Yeah. So what does it prove? What does he say? You take a family of subgroups of Z. So G0 equals Z, contains G1, G, a descending chain, infinite chain. And you define this. V of A is the maximum I such that A belongs to GI, okay, for A in Z, of course. I'm always working in Z. So you define this, and it turns out that it's a group valuation. It behaves like a bit like the periodic valuation, a bit less with less properties, but still good ones. And then it shows Z plus, okay, and then you define the order, right? X is less than Y if V of X is less than V of Y. Okay. And then it proves that this first, yeah, okay, it proves a lot of things. It's a very nice result, a set of results. I mean, yeah, this is dp minimal. Two, it proves that, so there are other kind of valuations. It proves that Z plus V is not necessarily minimal in the sense of expansion. So then there might be reduct if you choose the valuation in some ways that such that you have some kind of two chains intertwined, and then you will be able to define a new valuation which is strictly different. So this is not necessarily minimal, and it proves also. I think that's why I was talking about where it is. Yeah, the periodic variation are not maximal. It was known for a long time, and it proves that all Z, all of this kind. So of course, the periodic valuation are a particular case of this valuation. You just take the P to the N Z as a family of groups, and all of these structures have proper dp minimal expansions. Okay, so the rigidity we had for the periodic valuation, like this result of minimality, is not even something about valuations, because there are other kind of valuations that are much more complicated. And also, I mean, it has some nice other results, like you can say whenever this expansion is distal, for those who know what this say, or is not. And okay, so with the result of Clausen, turns out that it's not even clear that we can say something really meaningful, even in the realm of periodic valuations, or of evaluations in general. So I will draw a bit of a recap of what is known, and then I will end with the recent positive results on this classification. Okay, so I will start with the group of integers, and then I will have one expansion which is very well behaved, which is my favorite one, the Presburger structure. And then above there is nothing. Okay, so this is meant to represent dp minimal dp minimal expansions of Z. So here there is nothing. Here also there is nothing. It's minimal. Okay. Then we have this, the periodic valuations, and this is minimal also. There is nothing. It's min. But above, there are structures, dp minimal expansions, a few of them. Yeah. So not empty. Okay. There are elements here. Then, so this will be like for the, yeah, okay. So Z plus and in general, these non-periodic valuations, there might be things here. And there are also these above. Okay, so this, let's say, this is valuations. You see, valuations. This is order. Okay, and then on the domain of cyclical orders, then it's a bit of a mess. Okay, so Z plus and some C alpha already there at this level. There are a lot of them. Okay. I mean, here also there are uncontaminated evaluations. Each one has a proper dp minimal expansion, which is given by this so-called scalar expansion with many reducts here. And then again, there are even more dp minimal expansion. This is for cyclic orderings. Okay. So I will go now. I will pass to. So at first this was the picture, and now the picture has changed a lot in terms of complexity. Okay. So let's go to because we are not only having negative results on this field of research, but there are also positive results. And those are kind of recent. So first, last year, so Eran Alouf, he proved something very positive, very rigid concerning dp minimal expansions. He proved that the following are equivalent. Yeah, the following are equivalent. Sorry for my French. So Z is interdefinable with Z plus with the order. This is equivalent to Z defines an infinite subset of of the natural numbers. Yeah, dp minimum, yeah. Z, yeah, of course. dp minimum. And 3, Z does not eliminate there exists infinity, by which we mean that there exists a formula phi of x. This is one variable and some tuple, and some bi's, some tuples of elements, such that this defines always finite sets, but of growing size, like phi of z bi. Cardinality of this is finite and unbounded. Okay. Yeah. So it is really obvious for this structure. It's like you take a1 less to x less to a2, or just 0 and n, and this is a formula like phi of x n. And if you change the n, you will have longer and longer definable sets, but all of them are finite. It turns out that this precise condition is actually equivalent to being interdefinable with this, and it's a big result. It's a huge, it's a long paper, complicated and nice. Yeah. So in particular, all of the other they do eliminate all of the other expansion. They do eliminate there exists infinity, and so that's like the most positive result we have on Z on these minimal expansions. And there is also recent work where they So this is
Christian.
Yeah.
You should be wrapping. You should be wrapping up now.
Okay. Yeah, sorry, but yeah, I should say this properly. So it's gunidine and Ozakan, and they're also 2021, and they don't prove really this for the structure, but basically they prove that Z plus C alpha is minimal. They don't prove it for this one, but for another structure which is interdefinable with the cyclical ordering. According to Gunidine. Yeah, it's not written in the paper, but I asked him because
I thought their extension has new subsets of integers just on it.
No, it's actually definable. These Betty sequences.
But they add a predicate for a new subset of n. So how could it be interdefinable with this and also be?
No, is it for a new subset of n?
I thought when I mean that paper that the expansion they had a proper redux.
Yeah, but no.
I see what you're saying.
Yeah. No, it's not. Yeah. I think they closed it, by the way, by negation, something like this. Yeah. So this is nice. Okay. So here we have nothing. Okay. Yeah. And so there are also other results of Kani and others. Which is a bit connected, but it's not clear what is the relation between minimality, and so things are happening. And so to finish, what happens to the conjecture, right? So now the picture is a mess, but the common thing between these three sides is that there is it defines a topology on Z. And it's a non-discrete topology in all cases. So the conjecture now would be so this is do not eliminate the X infinity. So every dp minimal expansion of that does not eliminate the X infinity is does define as a definable group, defines a topology on the group, a group topology, which is non-discrete. Yeah. And yeah, and there are indices for how to prove this conjecture. It really looks a bit like Johnson's work, right? So in the proof of Johnson, but classification of the minimal fields, he uses strongly that there is infinity is something that you can say. So that's kind of the situation at the moment. Try to define a group topology using there is infinity. Okay, thank you. Sorry for the late. Okay.
Okay. Thank you, Christian. And I guess we can allow a quick question.
Yes, yes, Siegfried. Yep. What? Sorry? I think it would just expand the same valuation, and it's a yeah. Yeah. Yes. So this is stable. That just the group. What is it? Yeah, it's stable, and so it's kind of with what we said. The result of Gabe, it's a maximal stable dp minimal because it doesn't have a stable expansion, which is dp minimal. Yeah, none of them are stable here. And one of the second theorem I cited was that there are no expansion. You can be dp minimal and stable, but there are none except Z itself.
Okay, I think we should stop there. So thank you again, Christian. That was a very nice talk. And in 2 weeks, we have Ali Faiz Mohammadi. Is Ali there? Okay, so I can't tell him to make sure he sends us a title and abstract. Okay. Thanks, everybody.